Exploring deep learning, the power behind modern AI. Introduction. In the previous episode, we explored the world of machine learning, discussing its foundational concepts, various types of learning methods, and key algorithms. We also looked at how machine learning is applied across different industries, driving innovation and efficiency. Building on that knowledge, in today's episode, we will dive deeper into one of the most transformative areas within AI: deep learning. Deep learning has revolutionized fields such as computer vision, natural language processing, and robotics, enabling machines to achieve human-like performance in various tasks. This episode will cover the foundations of deep learning, the structure and function of neural networks, key architectures like convolutional neural networks, CNNs, and recurrent neural networks, RNNs, and their real-world applications. By the end of this video, you will have a comprehensive understanding of how deep learning is driving the AI revolution. What is deep learning? Deep learning is a subset of machine learning that uses neural networks with many layers to model complex patterns in data. These networks are inspired by the structure and function of the human brain, where interconnected neurons process information. Deep learning excels in tasks where traditional machine learning algorithms struggle, particularly in handling large volumes of unstructured data such as images, audio, and text. The term deep in deep learning refers to the use of multiple layers in the neural network. Each layer extracts increasingly complex features from the input data, allowing the network to learn hierarchical representations. This hierarchical learning is what gives deep learning its power, enabling it to perform tasks like image recognition and language translation with high accuracy. Neural networks, the building blocks of deep learning. Neural networks are the fundamental building blocks of deep learning. A neural network consists of layers of nodes, or neurons, that are connected by weighted edges. These weights are adjusted during training to minimize the error between the predicted output and the actual output. The basic structure of a neural network includes an input layer, one or more hidden layers, and an output layer. The input layer receives the raw data, the hidden layers process the data, and the output layer produces the final prediction. Each neuron in a layer performs a simple computation. It takes the weighted sum of its inputs, applies a nonlinear activation function, and passes the result to the next layer. This process continues until the data reaches the output layer, where a final decision or prediction is made. Activation functions play a crucial role in neural networks by introducing nonlinearity, allowing the network to model complex relationships in the data. Common activation functions include the sigmoid, ton, and ReLU, rectified linear unit. Training deep neural networks. Training a deep neural network involves adjusting the weights of the connections between neurons to minimize the difference between the predicted and actual outputs. This is done using a process called backpropagation, combined with an optimization algorithm like gradient descent. Backpropagation works by calculating the gradient of the loss function with respect to each weight in the network. This gradient tells us how much the weight needs to be adjusted to reduce the error. The optimization algorithm then updates the weights in the direction that reduces the error, iterating this process over many training examples until the network learns the task. One of the challenges in training deep networks is the vanishing gradient problem, where gradients become very small as they are backpropagated through many layers, making it difficult for the network to learn. Techniques such as using the ReLU activation function, which does not suffer as much from this issue, and layer normalization help mitigate this problem. Another challenge is overfitting, where the network performs well on the training data, but poorly on new, unseen data. Overfitting can be addressed using regularization techniques, such as dropout, where random neurons are dropped during training to prevent the network from becoming too reliant on any single neuron. Key architectures in deep learning. There are several types of neural network architectures, each designed to handle specific types of data and tasks. Let's explore some of the most important architectures in deep learning. Convolutional neural networks, CNNs. CNNs are specialized neural networks designed for processing grid-like data, such as images. They are particularly effective for tasks like image recognition, object detection, and video analysis. A CNN consists of multiple layers, including convolutional layers, pooling layers, and fully connected layers. The convolutional layers apply filters to the input image to detect features such as edges, textures, and shapes. These features are then passed through pooling layers, which reduce the spatial dimensions of the data, making the network more efficient. One of the key advantages of CNNs is their ability to automatically learn and extract features from raw data, eliminating the need for manual feature engineering. This has made CNNs the go-to architecture for many computer vision tasks. Recurrent neural networks, RNNs. RNNs are designed for sequential data, such as time series or language. Unlike traditional feed-forward networks, RNNs have connections that form cycles, allowing them to maintain a memory of previous inputs. This makes RNNs ideal for tasks where the order of the data matters, such as language modeling and speech recognition. The basic RNN architecture suffers from the vanishing gradient problem, making it difficult to learn long-term dependencies. To address this, more advanced variants like long short-term memory, LSTM, and gated recurrent units, GRU, have been developed. These architectures use gating mechanisms to control the flow of information, allowing them to capture long-term dependencies more effectively. RNNs have been widely used in natural language processing, NLP tasks, such as machine translation, text generation, and sentiment analysis. They have also been applied to other sequential data tasks, such as stock price prediction and anomaly detection in time series data. Generative adversarial networks, GANs. GANs are a class of neural networks used for generating new data that is similar to the training data. GANs consist of two networks, a generator and a discriminator. The generator creates fake data, while the discriminator evaluates whether the data is real or fake. The two networks are trained simultaneously in a game-like scenario where the generator tries to fool the discriminator, and the discriminator tries to correctly identify real versus fake data. GANs have been used to generate realistic images, videos, and even human-like text. They have also been applied in areas such as data augmentation, where they create synthetic data to improve the training of other models. One of the challenges in training GANs is maintaining the balance between the generator and discriminator. If one network becomes too strong, the training can become unstable. Various techniques, such as Wasserstein GANs, WGANs, have been developed to address these challenges. Autoencoders. Autoencoders are neural networks used for unsupervised learning, particularly for tasks like dimensionality reduction, denoising, and anomaly detection. An autoencoder consists of an encoder that compresses the input data into a lower dimensional representation, latent space, and a decoder that reconstructs the original data from this representation. The goal of an autoencoder is to learn an efficient encoding of the data, capturing its most important features. Autoencoders have been used for image compression, feature extraction, and even generating new data when combined with generative models. Variants of autoencoders, such as variational autoencoders, VAEs, extend the basic model to generate new samples from the learned distribution, making them useful for tasks like generating realistic images or filling in missing data. Deep learning in practice, applications, and case studies. Deep learning has been applied across a wide range of industries, driving innovation and transforming how we interact with technology. Let's explore some of the most impactful applications of deep learning. Computer vision. Deep learning has revolutionized computer vision, enabling machines to interpret and understand visual data with remarkable accuracy. Applications of computer vision include image classification, object detection, facial recognition, and medical image analysis. For example, in healthcare, CNNs are used to analyze medical images, such as X-rays and MRIs, to detect diseases like cancer or pneumonia. These models can assist doctors in making more accurate diagnoses and identifying conditions earlier. In the automotive industry, computer vision powered by deep learning is the foundation of autonomous vehicles. These systems use CNNs to process data from cameras and sensors, allowing the vehicle to detect and avoid obstacles, recognize traffic signs, and navigate roads safely. Natural language processing, NLP. NLP is another area where deep learning has made significant strides. RNNs, particularly LSTMs and GRUs, have been used to build models that can understand and generate human language. Applications of NLP include machine translation, sentiment analysis, chatbots, and voice assistants. For instance, Google's translation system uses deep neural networks to translate text between languages with high accuracy. Similarly, voice assistants like Amazon's Alexa and Apple's Siri rely on deep learning models to understand spoken commands and respond appropriately. In the legal industry, NLP models are used to analyze and summarize large volumes of legal documents, making it easier for lawyers to find relevant information and build cases. Speech recognition. Speech recognition systems convert spoken language into text, enabling voice-controlled interfaces and real-time transcription. Deep learning models, particularly RNNs and CNNs, have been instrumental in improving the accuracy of these systems. For example, Deep learning has powered the development of real-time transcription services used in meetings and conferences, allowing participants to receive accurate text versions of spoken words. These systems are also used in customer service, where they transcribe and analyze customer calls to provide better service. Robotics. Deep learning is also transforming the field of robotics, enabling robots to perceive their environment, make decisions, and perform complex tasks. Applications include industrial automation, healthcare robots, and autonomous drones. For example, in manufacturing, robots powered by deep learning can inspect products for defects, assemble parts with precision, and adapt to new tasks through reinforcement learning. In healthcare, robots are being developed to assist in surgeries, providing surgeons with enhanced precision and reducing the risk of errors. Challenges and future directions in deep learning. While deep learning has achieved remarkable success, it also faces significant challenges that need to be addressed to unlock its full potential. Data requirements. Deep learning models require large amounts of labeled data to achieve high performance. However, in many domains, labeled data is scarce or expensive to obtain. Techniques like transfer learning, where a model trained on one task is fine-tuned on a related task with less data, are helping to mitigate this challenge. Computational power. Training deep neural networks is computationally intensive, requiring powerful hardware like GPUs and TPUs. While these resources are becoming more accessible, the energy consumption and cost of training large models remain significant challenges. Interpretability. Deep learning models are often referred to as black boxes because their decision-making process is not easily interpretable. This lack of transparency can be problematic in critical applications like healthcare and finance, where understanding the rationale behind a decision is crucial. Bias and fairness. Like other AI models, deep learning models can inherit biases present in the training data, leading to unfair outcomes. Developing methods to detect and mitigate bias in deep learning models is an ongoing area of research. The future of deep learning. Despite these challenges, the future of deep learning is bright. Emerging trends include the development of more efficient architectures, such as transformer models, which have revolutionized NLP by improving the ability to handle long-range dependencies in text. Another promising direction is the integration of deep learning with other fields, such as neuroscience, to build more biologically inspired models. These models could offer new insights into how the brain processes information and lead to the development of more intelligent systems. Quantum computing also holds the potential to accelerate deep learning by providing unprecedented computational power, enabling the training of even more complex models. Conclusion. In this episode, we've explored the fascinating world of deep learning, from the basics of neural networks to advanced architectures like CNNs and RNNs and their real-world applications. Deep learning is at the heart of many of the AI technologies we interact with daily, and its impact on society will only continue to grow. In the next episode, we will dive into reinforcement learning, another key area of AI that focuses on how agents can learn to make decisions by interacting with their environment. We'll explore its applications in robotics, gameplaying, and beyond. Thank you for joining us on this deep dive into deep learning. Don't forget to subscribe and hit the notification bell to stay updated with our AI series. See you in the next episode.